All right, so let's come back to this Fenton-Rockefeller duality. So we have two convex functions. Okay, now then my Apple Pencil does not work out. Uh, what's going on? Okay, let me use my hand. Okay, hand does not work. Okay. Okay. Phew. Uh, so okay, let me just do it quickly. So we have two convex functions, and then we consider their Legendre Fenchel transform. And the Fenchel-Rockefeller duality says the infimum of the sum of convex functions is the same as supremum of this expression. This kind of a sum of negative of this Legendre transform, but you have this weird expression, negative z star here. Okay, but two things, actually three things, and this equality requires this assumption. Okay, then at least there is one point where this phi and psi are both finite. Okay, and at that point, we want this one of the function, just phi, to be continuous. Yes.
Is E star a convex set?
E star is a just whole space, so it says convex set. I said it's a vector space. Okay. Yeah. Right. Okay. And second thing is that this theta plus psi can be understood as the difference between theta and negative psi. So if you remember, we drew this picture that we have some convex function theta here, and negative psi is a concave function like this, and then this infimum is about the gap between these two functions, but this maximum, this is about the gap between these supporting linear functions to these convex and concave functions. And then you can, the point is that you can find some z star, yeah, exists z star, which corresponds to the slope of such parallel hyperplanes, that the gap between these hyperplanes is equal to the minimum gap or infimum gap between these two functions. So this is a picture illustrating what's going on in Fenchel-Rockefeller duality. Okay, so we established this theorem last time, and now we can use that theorem to prove our no duality gap theorem, this equality. So if you compare these two expressions here and there, okay, so we just want to translate these primal and dual problems into this form, okay? Then once we did that, then we would have this equation coming from this Fenchel-Rockefeller duality, okay? So now we just translate our optimal transport duality in this context of, in the context of Fenchel-Rockefeller duality. Okay, now, okay, I should ask. Okay, then you want to determine, let's say, in Fenchel-Rockefeller duality, let's say this is our primal problem. Okay, then you want to decide from this previous optimal transport primal dual, which problem between this P mu nu or T mu nu you want to put as the problem corresponding to this infimum of theta and psi. So do you understand my question?
Mm-hmm. Yeah.
Or you want to first decide which space corresponding to this primal problem and dual problem of optimal transport you want to choose as this space E. people in the Zoom, do you understand my question? You want me to repeat?
I got it.
But this is something belonging to the previous lecture. So let's just focus on my question at the moment. Okay.
I think it's related, right? You said detailed that.
No, it's more.
By
It could be related, but so here it is related to one of the questions some of you asked me after I think lecture 2 or something when I said, oh, the measures and functions are towards each other. Okay, and then that statement was not completely true. Okay, so the dual space of the space of continuous functions is the space of measures. Okay, especially when the underlying space is compact. But the dual space of the space of measures, it contains the space of continuous functions, but it can be bigger. Okay. Am I making sense? Maybe did that? Yeah, right. Okay. So dual space of continuous functions is a space of measures, but the opposite is not necessarily true. So that means we want to choose the space of continuous functions corresponding to this problem d theta as our kind of initial space for this Fencher-Rockefeller duality. Then this E star will be the space of measures, which are like space of transport planes. Okay, so that's why we choose E as the space of continuous functions or on this product space x times y, and then E star, which is the dual to it, is a space of signed Borel measures. Okay, and this is a result of so-called Ricci representation theorem, and you can check this book for that. Okay, so we start with this kind of dual problem of optimal transport, namely this d theta, as our starting point for the Fencher-Rockefeller duality. Okay. Okay, then here, then we want to choose this theta and psi corresponding to this expression, okay, and this constraint. Okay. So we want to right. So here, don't worry about this infimum and supremum being different because I mean you can just change the sign. Then infimum becomes supremum, supremum becomes infimum. So this is not a big deal. Okay, but let's just focus on this expression. So what theta and psi should we make to express these objective function and conditions fully? Okay. Let me give you an example. It's like this. So first of all, I cannot separate these two. So this is the answer. How does it go? So for this dual problem, d theta, or this problem d theta, we want to satisfy this constraint. Okay. So then we can achieve it. Sorry. But in this problem, in this Fencher-Rockefeller duality, the problem on the left, also the problem on the right, they do not have constraint by themselves, right? They do not have any constraint. They are just functions, and then you take in, right? They do not have such any constraint, only functions, okay? But on this problem we want to analyze, we have this constraint, and we learned the way to turn a constraint problem into unconstrained problem, right? By just adding penalty function to the original objective function. Okay, so that's what we are doing. So like, let's say we want to satisfy this condition, so we want to put some penalty to it. Let's say, first of all, we just want to have only one single function, u on cxy, but then this u, we want it to be expressed as this sum. This means u1 is uxy is ux is phi x plus psi y. Okay, we want it to be expressed in this way. Okay. Also, this expression, which is now after this, which is now u, has to be bigger than or equal to negative c. Okay. So we translate this constraint on the functions phi and psi into a constraint on the function u or on the product space x times y as this decomposition condition and this inequality. Okay. And we want those u satisfy these conditions. So then we give the penalty. So if it does not satisfy this inequality, we give this infinite penalty. So in this problem, we have negative here. So if you put infinite penalty here, we will get negative infinity, which is like a hard penalty. So the actual problem you just put as this phi plus psi, sorry, theta plus psi. This one, even though it does not have any constant itself, it automatically, those u's giving the infimum, giving the infimum values will automatically satisfy such constraint because of this infinite penalty. Okay, am I making sense here? I mean, before this exercise, just don't worry about this exercise yet, but just do you see my point that these penalty functions, I mean, you just add this penalty, like infinite penalty, if they don't satisfy this, then this sum will correspond to exactly this expression. I mean, with plus here. I mean, because I just turned supremum into infimum, or this, right? Am I making sense here? Okay. Yeah, don't worry about this yet. Okay. Do you agree? Or do you understand?
I'm just trying to keep track of E. Like
E
set,
is E is this
set.
continuous functions on the product space. Just the claim is that this expression, which is this, is the same as this expression coming from this theta and psi. Yes. We mean that, yes, because yeah, I cannot imagine any like very weird case. Yeah, just basic cases, because in, for example, in maximization problem, if you put negative infinite penalty, then you don't want to have negative infinity, so you will automatically satisfy the constraint. Okay, maybe, so yeah, basically the idea is to use this like a hard infinite penalty to turn this constraint problem into this unconstrained problem. But along the way, we just want to have some expression, the optimization problem over the space of continuous functions on the product space. Okay, so that's what I mean. But in the original problem detail that we had two functions, so we just express this two function condition into just one function condition. Okay. Okay. Now let's come back to this exercise. This function psi is kind of defined in a weird way. Okay, if this function is decomposable into this direct sum between two single variable functions, then it gives this value, otherwise cross infinity. So here, what you want to ask is if this condition, I mean, this expression is well defined. Because I'm asking this because, oh, you may think, oh, then such U may have different functions, phi, let's say phi theta, phi prime, and psi prime, making the sum into U. Then these expressions will, I mean, these values will be changed, right? Then how can then we have the same value for all possibly different phi and psi combination? Okay, so that is what this question is asking. Do you understand the question now? Okay, just simply why this expression is well defined. Here, this value will depend a priori, depend on theta and psi, right? But there might be different choice of theta and psi giving the same sum U, right? Then for those different phi and psi, you may have different, you will have different, you may have different values for these integrals. Then you may have different value. So then this function may not be well defined. Okay, am I making sense? Okay, then why is it well defined? What do you mean by constraint? Right. So what kind of properties this Jeff is saying, mu and nu have some conditions. What kind of conditions do they have? Finite? The finite is not sufficient. Yeah, so that means they have the same mass, or I think it's equivalent to saying it's a marginalization condition. So it's like this. Suppose you have different different phi prime. Let me use tilde. Phi tilde, phi tilde, and psi tilde. Right, and then okay, then the difference between this phi and phi tilde will be, you can just easily compute phi x minus phi tilde x with is psi y minus psi theta y, right? So on the left, you have function of x. On the right, you have function of y. When does this happen? Only when this either side is constant. So such different functions, they are different, but the difference is only an additive constant. Okay. Another thing is that additive constant, let's say C, is the same for both phi term and psi term. You have the same C. I mean, actually, if this is C, the other one will be, the other one should be negative C, right? Because their sum should be the same. So if you add C here, you have to subtract C there, right? So then if you go back to the integral, you have plus C and negative C here. So you have this additional term, integral of C with respect to mu and integral of C with respect to mu, and it's negative subtraction. But then this is constant. So this is the same as C times integral of mu minus integral of mu. But our condition was they have the same total mass. So it's 0. So this is why this expression is well defined. Okay. Okay. I think this is not so difficult. So you can just sit down and you can just finish do it. And why these functions are convex? You need convexity. I mean, to apply this Fencher-Rockefeller duality. Why are these convex? Right. So let me just repeat what he said. He's saying that, Young, you last time can explain this kind of general effect that if you have some convex set in your domain, and then if you consider the penalty function, just giving like let's say 0 inside the convex set and infinity outside, then such a function is a convex function. So the hard penalty coming from the convex constraint is a convex function. Okay, that's something you want to remember. So here is a set of U satisfying this condition. Is it convex? What is convexity? If you have U and another function U theta, and you make this any kind of linear combination between them, and if both satisfy this condition, then the linear combination will also satisfy, I mean, it's not linear combination, it's convex combination will also satisfy this, right? And what about this? If U satisfy some condition like this, and U theta satisfy phi theta plus psi theta, then U plus U theta, I mean, any like convex combination will satisfy, yeah, the same thing, right? Makes sense? Yeah, I mean, you know what I mean. So because these are like linear expressions, such conditions survive in convex combination. So that's why the set of functions satisfying this condition is convex. And then these are hard penalty for those convex sets over the convex sets, so they are convex functions. So okay, so they are satisfied.
Conditions on fire side being like convex or
Yeah, they are convex. I mean, in Fencher-Rockefeller duality, we need them to be convex. Okay, first of all. So we are checking those conditions. Leader phi. No, here they are just I mean we just translate this condition into these functions. Yeah. Okay, so now so then there's this remaining condition for Fencher-Rockefeller thingy. Okay, then we want to find such let's say Z0. So here as a particular function on this product space, okay? And we want it to satisfy this finiteness condition and this continuity. So that function, let's call in this context just U0. Okay, U0 is our Z0 in the vector calculator. So U0 is a particular continuous function on the product space, and it wants to make these values finite. That means U0 has to be bigger than or equal to negative C, first of all, okay? To get finite value, otherwise it will give infinite, right? So you want some function satisfying this constraint, also satisfying this constraint, okay? U0 has to satisfy both constraints, okay? And as U0, which one is it? Let's say this function is continuous. That means small change of U will make only small change on the value of this function. But then in our case, the value of this function is just constant. So that means a small change of U will not change this value. That means small change of U will still satisfy this constraint. Okay. So we want to choose such or identify or find such function U0 in the product space. Okay. What can be your candidate?
Maximum over all the guys
Okay, so what Jeff said is what exactly I'm going to say. So let me not repeat. Okay, let me just repeat what he said, but that's what I was going to say anyways, okay? So you want to satisfy this, but our space, we assume to be compact, right? Okay, so X and Y are compact. We assume that so you can actually take the maximum value of negative C, right? Right? So you can easily find such U just as that maximum value. Okay. Then it's a constant function. And you know that constant functions satisfy this condition trivially, right? This constant function is constant plus constant. Okay. So any constant function satisfies this condition. Good. And then if you choose the constant bigger than the maximum value of negative C, then it satisfies this condition too. And then the only remaining part is continuity. Means if you add some other small function to that constant function, you still want this inequality be satisfied. That means you want to choose your constant strictly bigger than the maximum value of this negative C. Then, so in other words, negative C will be like something like this. And then there is a maximum value here. You choose U0 to have this strictly larger value than this maximum value. Then if you make any small, sorry, yeah, let me just do it again. So you have, let's say, negative C, and this will have the maximum value. And then you choose your U0 as a constant function, strictly larger than this maximum value of negative C. Then if you make any small change to U0, okay, still this small change will be over negative C. But why do I why do I mention about this? Why do I consider these small changes? Because that's what is about continuity, right? That the function, this function, which is constant function, does not change with small change of this function, meaning the small change of this function still satisfies this condition, bigger than negative C. So you can just achieve it by just taking this. As I said, you take the maximum of this negative C, which is attained on this complex space. And you just add some positive constant. Okay, then this U0 will work for these conditions. Okay, I just explained this, but Just make sure you understand that. So these are your exercise. Okay, now we satisfied all the conditions for Fencher-Quaternion duality. So this infimum of this theta plus psi over this continuous function on the product space, the same as the maximum value of this expression. Here are two things. The value is the same as the supremum value on the of the right-hand side, and the supremum value is attained by some element in this dual space of the continuous functions. But the dual space of a continuous function, this is a measure on the product space, right? So dual of continuous functions is measures. All right. Okay, so now we know that the left-hand side was the same as basically the d theta, actually minus d theta. Okay, so then we just want to identify this right-hand side as a minus negative of the original optimal transport optimal value. Okay. Okay, so we want to check whether this problem is exactly whether it's exactly the same as the original optimal transport problem. Okay, that's what you want to check now. Am I making sense here? Okay. Question? Yeah, so we want to check whether this is the same as actually negative p mu. This is negative d theta mu. We just want to check. I mean, this is okay, but we want to check whether this right-hand side is the same as minus p. Okay, am I making sense? Okay, question from the Zoom. Okay, then we just need to check this Legendre-Fencher transform of this set times xi. Okay, so what is theta star minus pi? I mean, this expression. So this is the exact expression of the Legendre transform, right? This is a dual pairing. This is a dual pairing between u and negative pi, right? I mean, the dual pairing between functions and measures is nothing but the integral, right? So that is that. So this is exactly the Fencher the transform, and we just put negative pi here, and then here this is supremum problem, but it's theta. If you do not satisfy the corresponding constraint for theta, it will give plus infinity. So this negative theta is negative infinity, but then this is a supremum problem. So negative infinity will be ignored. So that means only the remaining functions satisfying this condition will apply to evaluate the supremum. So then for those functions satisfying this condition, this value is 0. That's why this is exactly the same as this. Okay, am I making sense? And you just want to play with this kind of argument just a few times. Then it will be it will be easy after that one. At first sight, it looks a bit weird, but so you need to just play with it at least a few times. Okay, for this type of argument. Right. So then you have this, but this supremum with the negative sign is the same as. Okay, I should. Okay, hold on a second. I want to turn this into this expression, which is basically the objective function of the original optimal transport problem. the transport cost. But look at this.
So right now, pi is just some element in that loop space. It's just some joint measure
Yeah, pi.
before that step.
Yeah, pi is this one. Yeah, so pi is here. So pi is
No restriction.
yeah, no restriction, just any signed measure even, okay? Not just a measure, signed measure. It can have both positive and negative signs, right? Okay, then here, so this is about u and pi, but you take supreme over all this, okay? Now, here, okay, do I want to leave it as an exercise or okay. Let me just do this, and then maybe I can skip the next one. Okay. 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 The claim is that this theta star is exactly the same as the transport whatever measure pi. Okay, and giving the condition that the sign measure is actually a measure, a negative measure, and the eventual Legendre transform of the other function psi, and after the similar argument, which will be just the same as the hard penalty for this marginal condition. Okay. Okay. So this is your exercise. Actually, both are your exercise. So maybe I can skip those. Okay. Do I want to do this now? Yes or no? If it is easy, I can skip it, right? Usually it takes more than what you actually need. I mean, I'm not that good at this kind of argument myself. Okay, so here, let's see. Let's just do this. So the claim is that this is the same as this. Okay, why? Look at the case when pi is negative at some point. Okay, like pi, just treat it as a function. Let's say the function is pi is a function of x and y. It's negative at some point. Okay, then what happens? If there's negative at some point, then at that point, minus of that is positive, right? Then here for u, the condition on u is that it has only lower bound. It does not have any upper bound, right? So if a value is positive, let's say this is the space of x and y, and let's say at x and y, if pi is positive somewhere, pi is negative elsewhere, then you can make this u concentrated on this part, and other part you can just make kind of 0. Okay, or even negative. Actually, C can be okay. At least you have to be bigger than negative C. Okay. For other part, you just make it as like something like negative C. But then at that point xy, some particular point x0 and y0, you make this function. Okay, then you can make this value go to infinity, right? That's what this says. Yeah, kind of. Yeah, so you just make the function concentrated on this particular point where this pi is non-negative, and then okay, so maybe this is not that easy because it requires some kind of analysis, and then there you make this this function, this particular test function u very large, then you can make this supremum go to infinity, and if pi is positive everywhere, then this is negative everywhere. Then to make supremum, you want to have U be as small as possible, right? That is exactly negative C, because negative C is the lower bound. That's why in that case, you can just put negative C here. So that's why you can turn this condition into this expression. Okay. Okay, yeah, the other, you can do some kind of similar argument for the other part. So, so we just have the following, that after this, if you add these together with negative sign, then you get here, negative of is negative of this, which is negative of that. So you get negative of C uh, integral d pi, and this condition is just here as a constraint. Okay, so you turn this problem, the right-hand side of the Fancher-Rockefeller duality, into this problem, which is exactly the same as the optimal transfer problem with this negative, with the opposite sign. Okay, so we just proved this no duality gap. Here, once again, Fancher-Rockefeller duality gives not only the equality between the infimum and supremum, but also it gives attainment on the right-hand side. Namely, you have an actual element in this dual space realizing this maximum value. That actual element is a measure on this space, okay, which is actually non-negative measure marginal conditions, right? So that is actually a transport plan, optimal transport plan. So this Fancher-Rockefeller theorem not only, I mean, it is kind of a way to, it not only shows the no duality gap, but it also shows the, the existence of an optimal solution of the original optimal transfer problem. Okay.
When you get that,
So that is in Fancher-Rockefeller duality. So in Fancher-Rockefeller duality, it used, if you remember, so the question was, why do you have such attainment? Okay, and then the answer is because the attainment is already in Fancher-Rockefeller duality here, and then they came from the fact. I mean, if you remember, the Fancher-Rockefeller duality used this what is the separation, hyperplane separation theorem, or yeah, Han-Banach theorem, or from Han-Banach theorem, which is about if you have two convex sets disjoint, then you can find a hyperplane separating these two. The existence of such hyperplane correspond to existence of the such maximum. If you really go through the proof of the Fancher-Rockefeller theorem, you realize that. Okay. All right. Okay, so now we finish this no duality gap. Now, yeah, I have 30 minutes. Okay, now, okay, we finished no duality gap, so we get so no duality gap plus attainment attain attainment attainment of p mu existence of optimal transport plan. Okay. Of course, existence of optimal transport plan can come from even more easy way. It is due to continuity of the objective function and the compactness of the space of probability measures over compact space. Okay? Just that, but we can view it also from this angle. All right, so we have no duality gap and attainment of the primal problem, optimal transport problem. And now, how do you get the attainment of the dual problem to the optimal transport? The dual problem is this. Okay. Okay, this also implies E mu nu, which is the is P, okay. P mu nu is bigger than or equal to d theta mu nu. I mean, because d theta mu nu had this additional continuity on the functions phi and psi. So you have always this is bigger than or equal to, and then this is always less than or equal to this P mu nu. So because this you have equality here, you have equality there. All right. So anyways, this is the dual problem now we can work on. And then we want to, we will show that this supremum is actually maximum. That means you will have this optimal dual solution. Okay. And the idea is this. So the space of continuous functions is too large, right? So I mean, the space does not have any compactness by itself. Namely, you can find there are many sequences in that space of functions, continuous functions that do not converge to anything, right? And for continuous functions to have convergence, you need some kind of more condition. And probably the most well-known condition to have such convergence or compactness of sequence is you learn this in your undergrad analysis course. The theorem is called, if you remember, Arjela-Ascoli theorem. So the Arjela-Ascoli theorem gives such a compactness, but to have Arjela-Ascoli theorem, we require a couple of conditions. What are they?
Equicontinuity, boundedness.
Yes, thank you. So first of all, the functions need to be bounded. The sequence of functions need to be uniformly bounded. Otherwise, you can just functions going to infinity without convergence. Okay, and is boundedness enough? No. Even if the functions are bounded between like two values, then the functions may oscillate too much, right? Then you may not have any convergence in the sequence of such functions. And the equicontinuity says it may oscillate, but the oscillation is not that is controlled in a uniform way. That's what equicontinuity says. So that means the shapes of the graph of the functions kind of behave in a controlled manner. They cannot change too much, and their change is kind of bounded. So they all have kind of similar shapes in a way. That's why you can get some kind of convergence. So that's the underlying principle we are going to use. So we will use Arjela. And then, but of course, I mean, these continuous functions do not have such properties for Arjela-Ascoli. And the idea is that, or important fact is that this supremum problem over all continuous functions can be further restricted to certain special class of functions, okay, which satisfy the conditions of Arjela-Ascoli, okay, and to learn that and to consider that, we will learn this so-called C-Legendre transform and C-convex functions first. Okay, so you can just read this. The point is that the C-Legendre transform and C will turn these functions into the functions we want, satisfying this boundedness and equicontinuity. Okay, especially equicontinuity. Okay, and C-convex functions are just result of C-Legendre transform. Okay, so terminology. Why C-Legendre transform C-convex functions? They are just generalization of Legendre transform and convex functions. Okay, You will see just in a moment. Okay. It's like this. C Legendre transform is exactly this expression. So if you compare the Legendre transform, which is just this. Yeah. This is expression of Legendre transform, right? Right. So here, instead of this dot product, we just put negative CXY. That's what C Legendre transform is. Okay. And here, X and Y may not be symmetric. So that's why for the other function psi, on the Y space, we use this different notation, C theta. But this C theta just comes from the same C. Okay. Okay, what is intuition? Remember, Legendre transform is like this. You have family of functions y to x dot y minus phi y. Which is as a function of y, it's just a linear function, and you have many such linear functions. And if you take supremum, you will get a convex function. Okay, that's why Legendre transform gives you a convex function. Here, the situation is similar. An example of C is like, let's say, let me just have x minus y square. Okay, just square function. Then the negative C x y minus phi x as a function of y looks like in the space of x, yeah, in the space of y, looks like some function like this kind of upside down parabola, right? Or paraboloid, right? This is just negative of this. So the graph looks like this. And then you have many such, and depending on your x, you have many such paraboloid, and then the C Legendre transform takes the supremum over all such family of functions. Okay. Okay. Am I making sense? So you just change in this picture this kind of affine linear functions into these kind of functions given by negative cxy minus this constant phi x. That's what the C Legendre transform does. And then all these inequalities are just the same as the Legendre transform. Okay. Question here? Any question? Okay. So once again, if C is the same as this negative dot product, then C Legendre transform is exactly the same as Legendre transform. And then Legendre transform have these nice properties, and these corresponding properties are satisfied by C Legendre transform. In particular, this kind of Young inequality for the C Legendre transform. Okay. Even for any C. Yeah, this inequality is just for any C. Look at this. This inequality, I mean, this is supremum. So if you do not take supremum, this value is bigger than or equal to any such right-hand side. So this is exactly this expression. Okay. Good. All right. So that's the form. And last time we played with this Jangda transform and these examples, and you can play with series Jangda transform with some particular examples to have some intuition of what's going on. Okay. Which one? Okay, so I suggest to do these two examples. Okay, so series Jangda transform of this is phi c of y is sup over in this case, let's just use the 1D case. Okay, let's just x in RD. And here C is okay, this was our C minus x minus y square over 2 minus is phi a dot x. Okay. Okay. What should be such a function? To understand this, you first want to consider this expression for each particular x. Okay. So now this is now function on the y space. Okay. Now at each particular x, okay, you have this like kind of principal term which gives you some upside down paraboloid like this. Okay. We center at x. Okay. Now this value will adjust the height. So depending on this value, it can be here or there. Okay. And this height is negative A transpose X. All right. Okay. Fine. Okay, then if you want to understand this, okay, so at each x, you have this value, negative A transpose X. Then you have the corresponding upside down hyperbole, upside down parabola. So this one is minus x minus y square over 2 minus A transpose X as a function of y. Okay. And then you have different x. At each x, you have something similar. The principal shape does not change, but the location of the center and the height changes, right? Making sense? Okay. Now, can you draw the graph of such function phi c after this? So you will have this family of such functions, right? And then this one will be the supreme over this family. Okay. Already suggest. But then to draw such family, you only need to, in this case, because all the shapes are equal, the same, you only need to chase this vertex of each parabola, right? What does this vertex do? So the x coordinate is x, and the y coordinate is negative a dot x, okay? So then this is nothing but the graph of this function, am I right? So then you first draw the graph of the function of the space of y. So then this negative a dot x should be, so let's say a dot x is like some function like this, and negative a dot x is like this, right? Negative a dot x, right? Right, you just upside down, passing through 0. And then you have these shapes having vertex point along this line. You have this shape, this shape, this shape, right? Get it? And then you take supremum, then all these shapes are the same. So it's like this one paraboloid sliding down or sliding along this this line. So then the resulting supremum will be just something like this. Yeah. So so this will be phi cy, while you have all these paraboloid sliding along this line. Okay, am I making sense here? Question. Now you can similarly compute the C-Legendre transform of this function. Okay. Yeah, with this cost function. Yeah.
Line in the dimension, but I don't understand why it's so.
In 1D
like a
is like
plane.
this. Yeah. In 2D you have like a paraboloid, okay, moving along this hyperplane. Okay, this vertex is moving along the hyperplane. So you have all the family. Imagine you have all the in kind of three-dimensional space, the space of the graph. You have this paraboloid moving along this hyperplane, right?
The distance that the king is governed by this like 1/2.
Right.
The not just the number probably, but have some different
So
stretching, squeezing.
yeah, the question is that this how can you imagine the even though this is like 1D picture, the question is how can you imagine a 2D picture? So in 2D you have some paraboloid like this, and this one, and then you have the 2D domain, and you have this R, and then you have this let's say hyperplane corresponding to is passed through 0, and it corresponds to the graph of a dot x. Then here basically you move this paraboloid where its vertex is on always on this hyperplane. Okay, so that's kind of the picture you want to imagine. Okay. Okay. All right. So okay. So as an exercise, do this in 1D case. So do it 1D. Okay. Then you have the so-called C-convex functions. C-convex functions are nothing but just the result of C-Legendre transform. It's like it's like convex functions are nothing but results of Legendre transform. Okay, and then you have all the same property for as the Legendre transform. So it's like a phi double star is phi if and only if phi is convex. And then you have this counterpart for C Legendre transform, and this is like phi triple star is the same as phi star for Legendre transform. Okay. So do this exercise. Okay. And then before I finish,
Excuse me, Professor, I have a question.
yes,
Are we assuming for this C transform, are we assuming any properties about the cost function?
at the
before-
moment, no. Yeah, so cost function can be anything for this,
Okay,
okay?
thank you.
Because here, all these things are just the supremum and this. There is basically no like analytic properties we require. However, in the next part, that's a very good question. The next part, I mean, we are doing this just to draw, remember, to draw some subset of continuous functions which have this nice compactness properties so that we can apply Ajalasco. So we want those functions continuous and uniformly bounded. Okay, and then the claim is that the C convex functions, the result of series Legendre transform, will be such functions, but of course not for any C, but for those C satisfying uniform continuity. If C satisfies uniform continuity, which is the same as continuity on this compact space X and Y, right? Then the C Legendre transform, the C convex functions, those resulting from C Legendre transform, all enjoy equicontinuity. Okay, where the modulus of continuity comes from the modulus of continuity of your cost function C. So this is what we have. So maybe I think because of time, I need to stop here. Okay, and so next time we will just briefly do this, discuss this part. Why, yes, why do we have equicontinuity of C Legendre transform when C has continuity, and why can we carry the modulus of continuity of C to its C Legendre transforms? Okay, so we will do that, and then after that, I mean, we can prove this dual attainment and so on. Okay, thank you for your attention. Let me stop now.
Thank you.